Hi Nine, I'm going to do a quick recap in terms of the video from yesterday about the types of radiation, and then we're going to look at the properties of each of them. Okay, so first of all, just a bit of a recap in terms of, I'm going to work isotopes. I'm going to move each of the words so that you can see them, okay, because obviously you won't be able to drag and drop them on the video, but you can try and figure out where they would all go. Okay, so there's 5 words, 5 spaces. Okay, so these are the words that would fit into the spaces. So see if you can figure out which words go where. Okay, so just pause the video and you can have a little go at that first. Right, those are the correct answers. Okay, so let's just go on to the next little bit that we want to. So yesterday we talked about the idea that some atoms are unstable. Okay, so some nuclei are unstable, and in order to become more stable, those nuclei will give out some sort of radiation. Okay, and it's completely random, it's completely spontaneous, but it's called radioactive decay. Okay, so the unstable nuclei will lose particles to try and help it become more stable. Now, there's 3 different types. Okay, we said that it's all random, it's all spontaneous, but it's this idea of decay. Okay, so the nucleus will change. Now, just in terms of, I don't know why it's not working, oh heck, we didn't want that. Just in terms of the 3 different types, we said that we've got alpha. An alpha particle is the equivalent of a helium nucleus. Okay, so it consists of 2 protons and 2 neutrons. Now, one thing that I didn't mention yesterday is that because it contains those 2 protons, an alpha particle has a positive charge. Okay, the neutrons don't have any charge, so that doesn't make any difference. But the fact that the alpha particle has got 2 protons in it gives it a positive charge. Okay, and this is the biggest of the 3 different types. Okay, still really, really small, but it is the biggest of the types of radioactive decay. Okay, and by losing this alpha particle, the nucleus becomes a little bit more stable. Now, the second type is beta. Okay, in beta decay, a neutron actually breaks into a proton and an electron. Okay, and the electron is emitted. So what you'll notice is in this nucleus here, if it starts again, the red neutron splits, it becomes a green proton, and that electron will be lost from the particle. Okay, so beta decay, because it is an electron, it contains a negative charge. Okay, so alpha is a positively charged radioactive decay, beta is a negatively charged radioactive decay. And then the last one is gamma radiation. This is not a particle. It doesn't have any substance to it. It's basically a wave of electromagnetic energy. Okay, so those is just a recap of the 3 different types. I'll just make it go a little bit further on. So like we said, you've got alpha. Okay, you've got these 2 protons and 2 neutrons. Now, and I'm doing these equations now, but we will practice them tomorrow. Okay, so when, in this case, it's radon, I think. Let me check my periodic table. What's Ra? 88. It's radium, sorry, my mistake. So radium, okay, radium has an atomic number of 88 and a mass number of 226. It gives out an alpha particle, so it loses 4 from its mass and 2 from its atomic number. So it becomes something else. Because the number of protons has gone down, it becomes a different element, and it becomes radon. Okay, but everything on the right hand side has to add up to what's on the left hand side, just like we've done in chemistry before. So my alpha particle is here. We draw it as a helium nucleus. Sometimes it's drawn as that funny little symbol. Okay, if I just go back up to it, this little symbol here, this funny looking A, sometimes it's drawn as that, but sometimes it's just drawn as a helium nucleus. Helium is 4 and 2. 4 plus 222 gives me my 226, and the 86 plus 2 gives me my 88. Okay, so they have to add up on either side. And I know what element this is because I can look it up from the number of protons at the bottom. Okay, so sometimes you do need to check, especially the high numbers. We're used to the sort of top of the periodic table. We're familiar with those elements, so sometimes you have to look up the ones that are more towards the bottom. So that's alpha radiation. Okay, don't need that. Right, beta radiation, like we said, you've got this neutron that becomes a proton and an electron. Okay, so in this case I've got a carbon isotope. This is carbon 14. Okay, this time my number of protons goes up by 1, but my mass number here becomes that -1, so that it adds up. Okay, so I've got carbon with a mass number of 14, proton number of 6. Because it gains an extra proton, that goes up to 7, which means I've got a -1 there, so 7 minus 1 gives me my 6. There's no mass, because electrons are so tiny, they don't weigh anything. Okay, so there's no mass included, so that's why the mass of an electron is 0, so the mass number stays the same. Okay, but because there's a different number of protons, carbon has decayed into an isotope of nitrogen. Okay, so that's what happens in these equations, but don't panic if you're still a bit confused, because we will practice them a little bit more. Where are we? Why is it not working? Right, so again, if you, no, I'm not going to do that, because the words will be, there's too many words. Right, gamma is this wave of radioactivity, tripping over my words, this wave of electromagnetic radiation. Okay, so there's no change in the number of protons or neutrons, there's no change in the mass. Okay, it's just giving out that wave of energy. So those are our 3 types. Now, what we need to think about is the properties of these types of radioactivity. Okay, now in terms of the size, alpha particles are the biggest. Okay, so when they bump into something, they transfer a lot of that energy, because they're moving very quickly, and they can affect the things that they bump into. So they will actually knock electrons out of other atoms, okay, and it makes it into an ion. So when an atom loses an electron, it becomes charged, like we've done in chemistry. Okay, so this is why it's called ionizing radiation, because each time the alpha particle bumps into another atom, it knocks out an electron, turns it into an ion, and it loses some of that energy. Okay, now they will have a big impact over a short distance, but they lose that energy really quickly, so that they can't go very far. So alpha particles can only travel a few centimetres of air, or they get stopped by paper, because they lose all their energy when they hit even something very thin. Okay, so alpha particles can't travel very far, but they will have an impact on the things that they do hit in that short distance. Now, beta particles, they can't ionize atoms as easily. Okay, so they're less ionizing, which means they can travel a little bit further. Okay, so this time beta particles can go through a few centimetres of air, and they can travel through something like paper. Okay, so they can actually travel straight through paper, but they will be stopped by like a thin sheet of aluminium, so like a drinks can. Okay, a thin sheet of aluminium, they won't be able to get into there. Now this is something that you just have to learn. I'll show you a summary at the end that you just need to know. Okay, now gamma, they are less ionizing, but they are very penetrative. Okay, so because it is because they're not passing on, they're not losing their energy to other atoms, it means that they keep that energy over long distances. So they can go through air, they can go through paper, they can go straight through aluminium without losing any energy at all. And they will keep going and keep going. And really they can be slowed down by a thick layer of lead or lots and lots of concrete. So gamma can really travel a long distance because it's not losing its energy to other atoms. It will keep going through materials. Okay, now I'll just go through this in terms of this is the classic experiment. So this is what we call a Geiger counter, and it will click, okay, in terms of, it makes a click noise when radioactive hits it. Okay, so if I can put, at the moment we're on alpha, if I put a piece of paper in between there, then my alpha particles get stopped even just by paper. They can travel through my, I can't get that out now. They'll travel through the air, but they can't travel through the paper. So the count has gone down to nothing. Okay, they definitely can't travel through aluminium. They can't travel through lead. either thin or thick, and they can't travel through your hand. Okay, so they will be stopped in a short distance. Now, if I move up to beta radiation, so let me just see what I need to do here. I need to reset it. Move on to beta. Again, I'll turn my Geiger counter on, so we're travelling towards that. They can go straight through paper. Okay, so they do not get stopped by paper. However, they will get stopped by aluminium foil. So you always work from the thinnest material that they'll go through to the thickest. Okay, so they will not, if they won't go through aluminium, they definitely won't go through thin lead. They won't go through thick lead. Your hand is normally counted like paper, so the beta radiation would go straight through your hand. So we often refer to paper and your hand as a similar thickness. I know they're not, but that's what we refer to them as. So I'll reset it now to gamma, if I can. Why is it not going on to gamma? Right, so this time we've got a wave rather than actual particles. Turn on my Geiger counter, go straight through paper, straight through aluminium, straight through thin lead, okay, although it's been slowed down, so I've got a bit of it going through. Thick lead, it will get stopped by, okay. My hand, it will just go straight through. Okay, so this is talking about the penetrating power of these different types of radiation. Okay, now this is the summary diagram that you need to be familiar with. Okay, so alpha will travel a little bit through air, but it gets stopped by paper. Beta will go through the air and paper, but it gets stopped by, sometimes they'll quote wood, aluminium, okay, thick card, something like that. It will get stopped by that. An X-ray is there as another example. So it goes through paper, goes through the aluminium, gets stopped by lead and thick metal. Gamma again gets stopped by thick metal. A neutron is a fourth type of radiation. We don't need to know too much about that, but that is the most penetrating, okay, because that will go through the lead as well. So alpha, beta and gamma, you need to be familiar with this diagram in terms of how much they can penetrate different materials, and that's what the work is going to be today. So your sheet is on class charts, okay. I know it keeps telling me that, but better look. So again, you can try and match these words up, so you can pause the video, and there's also a sheet on class charts for you to complete.